Okay, so check your charts with people around you, and then we're going to start graphing together. For right now, we're going to start graphing the sine of x function. And just so you know, for all of these graphs, we're going to do the sine, cosine, tangent today. Next class, we will do the cosecant, secant, and cotangent. These are known as our parent functions. Then we're going to do transformations on them. This whole unit kind of ties all together with the graphing. But we are going to start by graphing, and you'll see this over here on your graphs. Every graph is in terms of radians, so we're not going to be graphing in terms of degrees. So everything here is spaced out in radians. These graphs look a little bit different. They're set up on purpose to work better for sine, cosine, tangent graphs. Sinusoidal graphs is what we call them. But where we're going to get these tables, and I just want to see you to see how your sine, cosine, tangent graphs come about. And we're getting these tables all out of your charts. So right now, all we're going to look at is the radians at the top of your chart and then the sine values underneath them. So if I paired those up as x, y coordinates, I'm just going to write the first 5 down right now. Unless you're writing with pencil and are willing to erase, don't write with me right now because we're not going to use all of them. Our first value, our first radian is 0. At 0, the sine of 0 is 0. The next one in our chart, the radian is pi over 6, which is 30 degrees. At pi over 6, if you look at the sine value in your chart, what is it? 1/2. Okay. The next one is pi over 4. At pi over 4, your sine value is root 2 over 2. At pi over 3, your sine value is root 3 over 2. And at pi over 2 in your chart, your sine value is 1. Any issues with where we're getting those? Directly out of your chart, right? So it's the radians across the chart, the sines underneath it. Now, we need to know those values, but if you're anything like me, you're not graphing things that include square roots, because I'm certainly not going to be doing that. So we're only going to be reasonable in the numbers that we graph. In other words, I can't graph root 2 over 2, and I also can't graph root 3 over 2. So I'm getting rid of those. This is why I told you not to write with me. So that means after pi over 6, the next thing I'm going to graph is pi over 2, which was that 1. Now, remember our chart just gives us the first quadrant, right? We use the reference angles going around the circle and the sine values from our chart using positives and negatives to go around the rest of the circle. Now, look at the radians that we have left here once I have eliminated the other ones that weren't nice. Okay? I've got 0 and pi over 2, which just means I'm going to do all the quadrant ones, right? So after pi over 2, we're going to also have pi, 3 pi over 2, and 2 pi. What other reference angle are we going to use since the nice ones that are left are in that top section? What reference angle is the good one? The pi over 6 one, right? Okay, so what other pi over 6s do we have? What's between pi over 2 and pi in the second quadrant? Yeah, requires remembering that, right? Anyone remember what comes between pi over 2 and pi? That's a pi over 6. 5 pi over 6. Good. What's the one directly after pi in your unit circle? That's a pi over 6. 7 pi over 6. And what's the last one right before 2 pi? 11 pi over 6. These are going to be all of our nice ones. Now, just to give you a little bit of reassurance, we're not going to be memorizing this entire chart. Okay? So then where do we get the sine values? We get them directly from the 3 that we have to start up there, right? If the sine at 0 is 0, the sine at pi is 0, and the sine at 2 pi is 0. If the sine at pi over 2 is positive 1, what's the sine at 3 pi over 2? What's the sine at 3 pi over 2 if pi over 2 is positive 1? 3 pi over 2 is negative 1, right? And then the rest of them are going to be halves, right? Where is sine positive and where is sine negative? Which quadrants is it positive? Top 2, it's positive. Bottom 2, it's negative. So that means this one's going to be a half. This one's going to be negative a half. This one's going to be negative 1/2. All right, I'm going to pause here. Now, part of the issue on this is how to get from that table onto your graph, okay? Because we still have an XY axis here. The X is your radians and the Y's are your sine values. However, we're not used to counting in radians, right? So notice there's labels along the X-axis right there. Pi over 2, pi, 3 pi over 2, and 2 pi. So it's the quadrant ones, right? Now think in terms of fractions. Notice that between 0 and pi over 2, there are 3 blocks, right? So what is it implying that they are breaking each block into? If it's pi over 2, 3 blocks, what's 1 block? Pi over 6. So each block is a pi over 6, which means the first block is pi over 6. The second block is 2 pi over 6, which reduces to what? Pi over 3. The third block, how we got pi over 2, is 3 pi over 6, reduces to pi over 2. Then 4 pi over 6, which reduces to what? 2 pi over 3. And then what? What's the next one? 5 pi over 6. And then the last one I'll do here, 6 pi over 6, reduces to pi. So every block is a single pi over 6 in these graphs every time. All right? You don't have to put all that in, but I was just showing you as you count there. That will also help you to graph. So remember in this table, these are still ordered pairs. So what's the first point in my table? This is an easy question, people. 0, 0. There we go. 0, 0 is right in the middle, just like it always was. If I want to graph pi over 6 1/2, I go over to pi over 6, which we said is the first block, and up a half. Since they're saying that each block counts as a half here, that's going to be right there. Where's my next point, my third point? Pi over 2, up 1. So I go over to where it says pi over 2 is, and up to 1, and I draw another dot. Okay? Take a minute on your own papers and try to just graph the rest of those dots. I know that sounds ridiculous for me to give you a minute to do that, but you need to practice. All right, check yours against mine. Notice there at the end I made an arrow past the 2 pi. This is because, remember we said we can go around and around and around the unit circle and keep adding 2 pi to any angle as many times as we want, which means it keeps going and going and going. We call these sinusoidal or periodic functions. Periodic functions repeat themselves. So it's going to go through this same wave motion again and again and again, which is how we graph the negative side. So for the negative side, I really don't want you memorizing a bunch of points. This is logic right here, okay? If I start at 2 pi and go backwards, I go through the negatives and then through the positives, and I get back to 0. Someone tell me where I go next. Negatives. Then positives, and it gets back to 2 pi. Okay, so I'm literally just going to use the same pattern of the dots and take it backwards. So that means on the left side, I'm going to go over a block and down 1. At negative pi over 2, I'm going to go down to negative 1. And I'm going to use that same pattern going backwards here to get the negative side. So I am not memorizing points over here. I'm using the pattern going backwards. You do better at this kind of graphing the more you can follow patterns. So less of this is going to be just brute force memorization, and more of it's going to be following your patterns. The quicker you can do it, the better. Okay. Any questions about your sine function right now? We're going to do the other two that we're doing today a little bit quicker, okay? So what I'd like for you to do, and I'm going to help you get started on the cosine one, we're going to get started with the cosine nice points. So now on your chart, we're looking at the same radians again. Now we're looking at the middle row, the cosines. This time, instead of erasing some, we're just going to go for the nice ones to begin with. So at 0, what is your cosine value? 1. Look at your cosine values and tell me after that 1, what is the next nice cosine value at? It's a half, and where is it? Pi over 3, right? And then we're going to do pi over 2, at which the cosine is what? 0. So that means we're using the quadrant ones, and we're using which reference angle the whole way through for cosine? Pi over 3. So after pi over 3, what's the one in the second quadrant? The second quadrant is 2 pi over 3. Third quadrant is 4 pi over 3. And fourth quadrant is 5 pi over 3. Okay, take a minute and try to fill in the other cosine values using positives, negatives, all students take calculus, and the reference angles. And then graph if you've got that. All right, so there's where my right side of my cosine graph looks, or how my right side looks. If we use the same logic that we use to finish our sine graph, we go from cosine on the left or on the right side, which is a maximum, down to a minimum, back to a maximum. What's it going to do on the other side? It's going to finish that top half, right? And then go into the negatives. So I'm going to reflect this one across to finish the positives before it goes into the negatives. Which means my entire cosine graph is going to look like this. Which if you look at the two in comparison with each other, if you took your cosine graph and shifted it about 3 blocks this way, it would be your sine graph, right? If you took this point and shifted it to the middle. It's the exact same graph, it's just shifted off from each other. Okay. We're going to talk about some questions involving these in your notebooks in just a minute. But we're going to finish our tangent graph first. So once you're done, flip to the back. We're going to talk tangent, which is very much different than these two. There are 6 of these graphs. We said sine, cosine, tangent, and then the 3 reciprocals. You're going to see that they go in pairs. Sine and cosine will go together. Tangent and cotangent, its reciprocal, will go together. And then the other 2 reciprocals will go together. Okay. All right. I'm going to move in just a second to my tangent graph. We all have this one? Almost. No, almost? Okay. When you look at your tangent values, you can assume for each one, because you've noticed on all of these that we use the 4 or the 5 quadrant ones. 0, pi over 2, pi, 3 pi over 2, and 2 pi. That's really what we're going to use for all of those, but they each use a different reference angle. So in the sine graph, it uses the pi over 6s. In the cosine graph, it uses the pi over 3s. Any guess what the tangent one's going to use? Pi over 4s. Okay? There's a small bit of logic to that stuff, right? So when I look at the tangent one, remember again that we're looking for the nice numbers out of our chart. So the first thing I see in my chart is that tangent of 0 is 0. The next nice one for tangent that I see is pi over 4, which is what? 1. And then the last kind of nice one, which you guys might not say is nice but is useful to us, is at pi over 2. And at pi over 2, what's the tangent? Undefined. That's actually helpful to us as we graph. So let's see what other values we want to fill in for our tangent table. We want 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then we said we're using which reference angle this time? The pi over 4s. So what's in the second quadrant between pi over 2 and pi? Three pi over 4? Which one's in the third quadrant? 5 pi over 4. And which one is in the fourth quadrant? 7 pi over 4. Take a minute, and this time I don't want you to graph. I just want you to fill in these extra points. All right, so when we go ahead to graph this, we're actually going to graph what you would consider the oddest thing first, and that's the undefines. Anyone else remember where we've graphed undefined in the past?
No.
Back in chapter 3, we did rational functions that had asymptotes. That's what undefines are. Undefines are vertical asymptotes, okay? So that means anywhere I see an undefined, which I see at pi over 2 and 3 pi over 2, I'm going to go ahead and graph a vertical dotted line asymptote, which means our graphs are not going to touch these points. Now, I want to graph all of those first, which means I have to predict the negative side right here. Look at the spacing. Keep in mind these are all very symmetrical. Where should I put my asymptotes on the negative side? Negative pi over 2 and negative 3 pi over 2. Here's a dead giveaway to a wrong graph when you're doing one of these. Your spacing between your asymptotes should be the same for every single one. If you have two asymptotes that are closer together than another one, you've done something wrong. These all have to be even. Now, before we can graph anything else, we also have to discuss the pi over 4 business with graphing. If you look back at your sine graph, we labeled and we said everything was counting by pi over 6s, right? So it's pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, pi. Did we anywhere see pi over 4s? No, right? So remember in your first quadrant, we said 0 is on the x-axis, pi over 2 is on the y-axis. Where did pi over 4 fall? Directly in the middle. So if I look at 0 being here and pi over 2 being here, where's directly in the middle of that? Right there. So that's going to be pi over 4. That means for the second quadrant, the 3 pi over 4 is going to be directly between those two. And 5 pi over 4 is going to be directly between those two, and so on. So it's going to be a block and a half in between the big ones, basically, every time. So I'm going to mark those first. If you want to mark them the whole way through, you can. Then I'm actually going to graph this set of points first. Okay. That set of points is going to give me a good picture of what one of them looks like, because if you notice, if I started at 0, I only kind of have one section of that middle section since it goes all the way over to negative pi over 2. So at 3 pi over 4, I have the point negative 1. 3 pi over 4 is between pi over 2 and pi, so right here. At pi, I have 0. And at 5 pi over 4, which is between pi and 3 pi over 2, I have positive 1. So this is a mini picture of what this graph is going to look like. It does not make a straight line, okay? And remember, you can't cross asymptotes. So what these make are S-shapes, which looks something like this. Sometimes I think I'm in like little kid world too much, but these always remind me of my little kids' rubber stamps, because this is kind of how you need to think on graphing this. This is literally stamped in every section, okay? And I tell you that because there's always someone that wants to flip them backwards when you go on the negative sides, okay? If you notice at 0, you have the point 0, and then at pi over 4, you have 1. That means in this middle section, which point am I missing, the positive 1 or the negative 1? I'm missing the negative 1, which is going to go over here. So that's kind of what I mean by the whole rubber stamping thing, that it's literally the same section of the graph repeated here, here, here. So at some point, once I get one of those, here's how I graph. In the middle of the section goes 0, positive 1's on the right, negative 1's on the left. I don't even look at my points. Middle of the section is 0, right is positive 1, left is negative 1, which would be over here. Middle of the section is 0, right is positive 1, left is negative 1. So once I get the picture for one of them, it repeats again and again. It does not reverse or change or anything like that. It just continues to do the exact same thing. We're going to do transformations of the sine and the cosine graph. It's very difficult to do transformations of these kind because of the asymptotes. Okay. Any questions about those three graphs, where they came from? I know that's kind of a lengthy, like me talking to you time, but it kind of helps to get the idea of where they come from. Now, in your homework, you're going to see we are not memorizing these big old tables here. You can memorize some basic points. You can get those tables anytime you want out of your chart. That's why I showed you that, if you want more points. I personally will memorize the tables that are in the homework, and you'll see that here in a minute. But before we do that, find your notebooks and flip to page 114. On page 114, the first thing that I want to talk about is under number 4. The beginning stuff up there talks about how to graph it on a calculator. We are not even messing with that. It actually makes life harder for you to try to figure the stuff out off a calculator. It's one of the few things that someone actually tried one year and then agreed with me on. They're like, yeah, calculators for this doesn't help you. One thing that we talked about real briefly was that sine and cosine are called periodic functions. Therefore, something we measure on each of these kind of functions is the period of the function. We say the period of the function is 2 pi, and here is why. It's basically how long it takes for it to complete a full rotation. So remember the sine graph, and you have this on your other paper, but I'm just going to draw you a quick sketch. I told you at 2 pi here, I draw an arrow because it keeps going, right? This is because from 0 to 2 pi, it goes through the positives, it goes through the negatives, and it comes back to 0, right? What's it going to do after 2 pi? The same thing again. So it goes through the positives, it goes through the negatives, comes back to 0. So that's why we say the period of the function is 2 pi, because it takes 2 pi from 0 to 2 pi for it to complete one cycle. Then it repeats in the second cycle, and so on. So when you say the period of the function, you're saying how long it takes to do one cycle of that graph. Okay? Some of these questions are going to be easier than others. I'm going to go through a couple of the easy ones to begin with here, and then there's some notation that we have to talk about here that's a little different. If you look at your sine graph, we have a maximum value and we have a minimum value. What is the highest y value that your sine graph gets to? 1. What is the lowest y value that your sine graph gets to? -1. Not super difficult. That also tells me out of number 7 that my range is what? -1 to 1 with brackets. Okay? Now, where does it reach its maximum? That is where we get into a notation thing. Okay? So, when it asks where it reaches its maximum, it's asking for an x value. In other words, what x value does that maximum line up with? So on your sine graph, where does that maximum happen for the first time? Pi over 2. Now here is the issue with these. Just because of how we've been taught to do stuff, we want to automatically list them out. So you'll look at that graph and tell me, well, there's one at pi over 2, there's one at 3 pi over, or one at -3 pi over 2, and then that will be your answer. Well, what did we say about these graphs? What do the arrows at the ends mean? They keep going and going and going. So can I really list out all of the maximums? No, nor do I actually want to. Okay? If it gets to a maximum at pi over 2, and you don't have this extension to your graph, but use my graph to think about it, when is the next time, or how long after that maximum is it going to get to another maximum? What's going to be the distance between the two maximums? 2 pi. Why is it 2 pi? Because it takes 2 pi, according to the period, to do a full cycle. That means it can be a full cycle from 0, positives, negatives, back to 0. You can also count a full cycle as maximum to maximum. Okay? So, how we're going to notate that then is you are going to do this, and I'm going to explain to you what this means in a second. After the single maximum that you're choosing, you're going to put plus or minus 2 pi k. The k is a constant, and it's because if I took that k out, here's what this says. There's a maximum at pi over 2. There's one forward 2 pi, and there's one backwards 2 pi, but that's it. Is that true? No, there's one forwards 2 pi, and another 2 pi, and another 2 pi, and another 2 pi. So that k is just there to say as many times forwards or backwards as you need to go. Okay? So let's use that notation for a minimum as well. The minimum was right here. Where did that fall on your graph? At 3 pi over 2. And because the maximum occurs every 2 pi, you can also assume the minimum occurs every 2 pi. So I'll put plus or minus 2 pi k. Now, what if you picked a different maximum or minimum than me? There's another one on your graph, right? There's another maximum at negative 3 pi over 2, and there's another minimum at negative pi over 2. I don't care. Pick a maximum, pick a minimum, that's fine. I picked the first positive one because it makes my life a little bit easier, I think. But that is the same way we're going to write our x-intercepts in a minute as well. Okay? Domain for this is very easy. I've skipped that. How far does it go to the left and to the right? Forever. Negative infinity to infinity, or all real numbers. X-intercepts, we're going to write the same way we write where the maximum and minimums occur. Where is one x-intercept on this graph? 0. Now, before you answer this question, think a minute. We then need to see how often on the graph the x-intercepts occur. Here's an x-intercept. Where's the next one? Pi, and then 2 pi, and then another pi, and then another pi. So how often does it take for another x-intercept to happen? Plus or minus pi k. Because there's 2 x-intercepts in each cycle, basically. Okay. Y-intercepts are not tricky. There's one y-intercept. Where does it cross? 0, 0. I just put 0. And then this is throwing it back to like unit 2, even and odd functions. Even means that it's the exact same thing over the y-axis. So what that means is, I'm going to show you in visual form for your sine graph. Your sine graph looked like this on the right side. It means on the left side that I can take this and it's copied right here. No. Is that the truth? No. That makes sine what kind of function? Odd. It's odd when you can say this section is reflected underneath over here. Okay, that's what an odd function looks like. Okay, now we're going to answer these same questions for our cosine, but I'm not going to walk through every single one with you. You might not get all of them right away, but flip to page 116 and try these same questions for your cosine graph. All right, so there's some of the easy stuff filled in. Where is one place that the cosine graph reaches a maximum? At 2 pi, so you could start with 2 pi and say plus or minus 2 pi k, because it occurs every pi before and after that. Where is another place that you could have said it reaches a maximum? 0. So both of these would be perfectly fine answers for that same question. I probably would have done this one because I see 0 first. Where's one place that it reaches a minimum? At pi. And it will reach another minimum every 2 pi before and after that. So the cosine graph then crosses the x-axis. Where's one good place for that? Pi over 2. And it's going to do that every how often? Pi k. Because the next one's at 3 pi over 2. You can subtract the distance between the two of them. Okay. All right, we're going to finish up with the tangent ones, which is 118. That will be the end of our notes for today. You're going to see for the tangent question, so your tangent questions here. The first thing is the period of the function. And we have to think about this one before we answer it. Remember, your tangent graph was these S shapes, right? And the period of the function is basically how long it takes to do one cycle of it. Well, each section between asymptotes is one section of the tangent graph, right? So you can say, what is the distance between these two asymptotes? Well, negative pi over 2 on one side, positive pi over 2 on the other. What is the distance between that? Pi. So the tangent graph has a period of pi rather than 2 pi. And that's again where my mental picture of that being a rubber stamp kind of comes into play. That one section, if I isolate it, can be a representation of every other section. I can take that one section and copy it again and again and again. So that's what tells me it's the period. The vertical asymptotes we're going to write very much the same way as we did the maximums, minimums, and x-intercepts, because again, you don't want to write them going out, out, out. So where is one, on that picture, where is one vertical asymptote? Pi over 2, and how often do they happen? Pi k. Domain for this is tricky. Not really, but we're just going to come back to it in just a second. Range. In each of those S shapes, where does it go on the bottom? Negative infinity in the top. Positive infinity. X-intercepts, where's one place that this crosses the x-axis? At 0, and then every how often after that? Pi k. Where does it cross the y-axis? 0. And would this be considered even or odd based off of its picture? Odd. Because again, directly to the right of the y-axis, we have a positive section. Directly to the left, we have a negative. So that reflection is an odd. Now your domain. Think back. Again, thinking back to before Christmas makes our brains hurt. But think back to when we did the rational functions that we talked about with the asymptotes. We had the graphs that look like these. And we said your domain for that is all real numbers, but x does not equal, and what did we leave out of that? The asymptotes, right? This is exactly how we're going to write our domain here. So I'm going to say my domain is all real numbers, but x does not equal. How have we represented our asymptotes now? We represented it right above that, right? So I'm going to say that's why we did the vertical asymptotes, actually. So that is how I write my domain. I'm leaving out every single asymptote in that small statement there. That's one of the main reasons we learn that notation, so that you can leave out every asymptote in one statement rather than saying x does not equal pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, and keeping on counting out. Okay? Now your homework for this section, like I said, is very short. Notes are a little bit longer, homework is short. This page right here, 119, 120, we are only doing questions 1 through 4. Now, here's my caution on this. I am 100% aware that you can complete questions 1, 2, and 3 by copying this page we just did in our notes. All right. Is that the best idea, considering you're going to have a quiz where you have to replicate all 6 graphs? Of course not. Of course not. Here's what I would like for you to practice in your homework, because I know this is just repeating the same thing. I would like you to practice memorizing these 5 points, okay? These are really the points you need to know for the sine graph. Like I can tell you 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, 2 pi 0, because that gives me the sine rotation right there. I know those still from when I had done this back in high school, because I had to do that. Then you can just do the backwards rotation for back here. So rather than memorize those larger tables, because you don't really need the half values, okay? Really, for this one, I need to know where it crosses 0, where it hits a max, and where it hits a min. That's all I need to know. On the tangent graph, you need to know where the asymptotes are, and then for me, where 0 is, because that gives me enough to do an S shape. That's it, okay? Now, the only other thing I'm going to tell you on your homework is this. You'd think we could read directions by 11th and 12th grade, but we can't. On question 4, It's the only different graph that we have to do. It asks you to graph sine and cosine just between 0 and 2 pi. So there you don't have to do arrows. You can stop here and here. Notice it says using 2 different colors. It's in there because it makes your questions a whole lot easier if you do that. And you can recognize which one is which, because they're going to intersect each other and they're going to look a whole lot like each other in that section. So you just want to answer some of these basic questions about where one function is higher than the other, where they're equal to each other, and so on, using your sine and cosine graphs.